Alright, here's an example on optimization. What I think the hardest part is for a lot of people is kind of taking the story, taking all the words and putting it into equations. Once you get them into equations, they're not horrible, although sometimes they can be kind of tricky. So what I try to do is I try to kind of depict what's going on with the words, with the picture over here. I'm not a great artist, but what I'm going for here is we have this hemisphere of radius 8 sitting on a horizontal plane. So that's this blue sphere or half sphere maybe. So you're picturing like a basketball cut in half sitting on a table. So that's what I got in blue here. And then we have a cylinder standing with its axis vertical, the center of its base at the center of the sphere, and the top circular rim touching the hemisphere. Okay, all that means is that you have this cylinder on the inside here that's sort of centered in the middle, and it's the top of it touches the top of the basketball. Right, so that's kind of this picture right here. And what we want to do is find the radius and height of the cylinder. So we're just finding information about this red object in here to maximize this red object's volume. It's pretty hard to work with this picture here. I think it becomes a lot easier if you think about what's going on here in 2 dimensions instead of 3. So maybe kind of picture, pretty terrible circle. Picture you take this and you kind of cut it vertically right down the middle. So this hemisphere we used to have in 3 dimensions, we now have in 2 dimensions, and the sphere sort of looks like a circle. This dotted line is sort of where it would go if it dipped under the table, but in fact it stops here. And then inside this guy we got our cylinder with the top of the cylinder touching the top of the sphere here. And really what the question becomes is we want to make this cylinder in here, which is depicted in 2 dimensions, as big as possible. So do we want something relatively short and fat like this guy? Or perhaps something we give up a little bit in radius, we make it a little skinnier, but then we are able to make it taller. So the question is the green thing here, does the green thing here have bigger volume, or does the red thing here have bigger volume? So if you sort of understand that idea, we can start attacking the problem. The first thing is you need to know the formula for the volume of a cylinder, because what we're trying to do is maximize the volume of the cylinder. So the thing that we want to maximize, the function we want to maximize, is the volume of the cylinder, pi r squared h. Maybe you remember that from geometry, that the volume of a cylinder is given by this equation right here. You can think of the pi r squared as the area of the circle on the bottom, and the h kind of the how many circles you got going up. So this is the derivative we'll want to take. The problem is it's got 2 variables in here, an r and an h. And we only know how to do single variable calculus at this point. So what we need to do is find some sort of equation relating the r and the h. And so the piece of information that we haven't used yet is that this cylinder has to touch the hemisphere. Or maybe in this picture, these corners right here, we'll use the red one, fall on this circle right here. So if you want to think about this as a circle that we know the equation of, you can put your axes right here and note that this point right here is at 8, 0, because we're given in the problem that the radius of the sphere is 8. So the distance out to this blue circle is 8. And then the other thing to note is this point right here we can think of as r comma h. What I mean by that is its x-coordinate, this distance right here, is the exact same as the radius of the cylinder. So it takes a little getting used to thinking geometrically to convince yourself of that, but maybe once you do that, you can see that this is r, and height kind of goes the same way. This height right here, the y-coordinate, we can think of as h. So that makes this point right here r comma h, and the thing to note about this point is it falls on the circle. So you're sort of thinking about it as the corner of the red rectangle, and then realizing that that corner of the red rectangle is also on the blue circle. And so if you remember the equation for a circle centered at the origin, what you get is x squared plus y squared equals, in this case, 64, the radius of the circle squared. So since our x's are r's, we can say r squared plus h squared equals 64. And so this equation right here, what I call the constraint, is what we will use to change this function that we want to maximize into a function of one variable. So we need to either get rid of the r's or get rid of the h's. If you're really clever, you might notice that there's an r squared in this equation. So rather than solving this guy for r, maybe we solve it for r squared. That is, subtract h squared from both sides. So then instead of plugging in for r, we can actually plug in for this whole thing, this r squared, what we have solved for here. So what we get is volume is equal to pi times, and then instead of writing r squared, I can write 64 minus h squared times h. I want to point out that if you had solved for r and then squared that, you'd end up back at the same point. We're kind of cutting out a step by getting a little bit clever and solving for r squared here. So anyways, this is our volume. Maybe there's a better way to write it. We can distribute the h through. So pi 64h. Maybe distribute the pi through also while we're here. Pi h cubed. And we get this thing right here is our volume. And since we're trying to find the maximum volume, we want to find a critical point. So we take the derivative and set it equal to 0. The derivative of pi times 64 times h is 64 pi. And the derivative of negative pi h cubed is minus 3 pi h squared. So what we want to do is take the derivative and set it equal to 0. So we got 64 pi minus 3 pi h squared is equal to 0. And solve for h. We got a pi in both terms, so maybe we divide both sides of the equation by pi, simplify things a little bit, get to here. And then to solve for h, let's add 3h squared to the other side, and we get 3h squared equals 64. So therefore, h squared is 64 thirds. So h is equal to plus or minus the square root of 64 thirds. But we don't want our height to be negative, so we can ignore the negative solution here and just call our height the square root of 64 over 3. And you might notice that square root of 64 is 8. So if you really want, you can simplify a little bit. You get rid of the radical in the denominator, but frankly I'm fine with it just like this. So maybe we'll call this thing h. This is our optimal height. Actually, I guess I should be a little bit careful there. This is a height at which there is a critical point, but we don't necessarily know that that critical point is a maximum or a minimum, or maybe it's just an inflection point at this point. So the way we can figure that out is by looking at the second derivative. The second derivative of this is all 0. Over here you get negative 6 pi h. And so if you stick in a positive number here for h, then you'll have a negative times a positive, which is a negative. So we got maybe v double prime of 8 over root 3 is in fact less than 0, which tells us that it's concave down, meaning our critical point has a shape kind of like this, and it's a maximum. So in fact, this was the solution we were looking for. But all we found is h so far, right? We haven't, the question asks for the radius and the height of the cylinder of maximum volume. So we're halfway done with the height here, and now we need to find the radius. What's nice to know is we have a formula right here that gives us the radius in terms of the height. So you could plug in this for h, but again we can get a little bit clever and note that there's h squares in the equation, so we can plug in 4h squared, which we have one line above here. That is, we can say that r squared, switch colors here, is 64 minus, and then instead of writing h squared, you can write what h squared is, 64 over 3. If you get a common denominator here, you'll get r squared is 128 thirds. So therefore r equals plus or minus square root of 128 over 3. Again, we don't want our radius to be negative, we want the positive solution, so you can ignore the negative and call it square root of 128 over 3. I guess since I simplified this one a little bit, I could simplify this, although really this is perfectly fine the way it is. But if you note that 128 is 64 times 2, then what you really have here is root 64 times root 2 over root 3. Root 64 is 8. So you got r equals 8 root 2 divided by root 3. I think that's just about simple enough. So we'll call this our answer for r and this our answer for h. And that is the end of the optimization example.